So is this good? Okay, wonderful. So the talk I'm going to be giving today is on biofilm-based passive technologies, their potential role in closing the gap towards achieving SDGs. I realize most of you in this group, maybe students in our under WASH Canada CREATE program focusing on low resource kind of. I'll share a broad concept of my research, but I will focus because I also do specifically research in this area. So I will present specifically that part of my research. That way, you can see some synergy in things that we do here and to relate to the work that you are doing there. So again, I will start the presentation just quickly, share with you what are the drivers for most of this wastewater research and specifically for our research here. And I kind of wanted to share this because I feel like it's important aspect. Somehow a mind teaser, it's kind of a new stressor to our industry, climate change. I like to share a little bit in depth on that from a problem aspect. Then I will deep dive into the type of technology that we are developing. This technology is being developed together with my industrial partner, Biofilm-Based. They developed the technology, I developed the process for that technology. So it was an amazing partnership between this company and us. We have been working on this for the last 6 years. And they are located off of Ottawa area. And I would probably close this whole talk by letting you guys know where the group is planning to go with this specific work. So in terms of the drivers for wastewater research, these are the common things that most wastewater engineers would know. We have a population increase, urbanization, and stringent effluent discharge criteria requirements. Oftentimes, this pushes into pretty much like expanding a treatment plant. When these things combine, the existing treatment plant is not enough. So the traditional approach had been every time there are the first 3 stressors or the first 3 drivers, we keep building, So if you see here, actually, this is coming from the picture here is coming from a Greenway wastewater treatment plant here in London, Ontario. We have 5 of them, by the way, which is amazing for a small, for relatively a small town like City of London. But this is the biggest where we get 70% of the flow too. So what you see here on the left-hand side, it was built back in 1950. As the population expands, then we added the second one, we call it section 2, and then they added a third one, you don't see it here, section 3, but now there is no room to expand. So this is the driver. Now there is no more land mass available because this is already actually close to very downtown London. There is nowhere to go. And when you have these drivers, what do you do? That's where my research really comes, intensification technologies. What intensification technologies do is they enable these existing infrastructures achieve 2x, 3x sometimes than they could have without these technologies. So I take it very seriously because it's really impactful to develop these things because it's a lot of saving from every aspect, not just money, but land mass, and other things. So now this has been the driver for the last 50 years, to be honest, in terms of wastewater processes and technologies. Now we have a newbie in the corner, which is climate change. And people would say, why climate change? Climate change probably has nothing to do with wastewater, The wastewater comes through sewer lines. What does it have to do with the climate? It comes from our home, debatable. So I look at climate change from 2 perspectives, not just myself, but a lot of people working in this area of research. One is, of course, how does wastewater treatment plants contribute to climate change, right? We do have emissions, and aspects of that need to be addressed. So that is a concept that we call a mitigation of climate change. The other one is adaptation, which is actually climate change impacts wastewater. Let's see how. So these are different categories. I would start mostly looking at the two right-hand sides. So with climate change, there would be flooding potentially. We are seeing that everywhere in the world, extreme weather would causing at times flooding, at times power outage together. So this at least, two things would impact wastewater travel. So if you have flood, because majority of wastewater plants are built by nature of them because they have to discharge to a freshwater body like rivers. They are built close to rivers in the low-lying areas. That's just, if you go now that you go and see wherever you are, where your wastewater treatment plant is, that's where majority of them design. So whenever there is flooding, it is potential that they will be the first infrastructure to be flooded. So with flooding, basically there is huge loss of everything, of course, if it happens. And then there is power outage, which would impact your process efficiency. If I just leave the other two for now, and then if I show you guys some of the example. So you can see here, I tried to get one from BC. So no, I do not know. I didn't get the chance to see where it is, but there was one that happened back in 2021, flooding of Merritt, BC. That's and then the flooding in Texas, which is a big one, which left about 40 wastewater treatment plants down, literally. And 7 of them were actually inoperable even after 1 month of hurricane. So you can imagine what that means, right? What goes into freshwater bodies with these systems being down. That's why I feel like this is really a big issue that needs attention, because as we are seeing this more and more, I think it's important to somehow talk about it and be able to come up with a solution to that. I can show you what the City of London does with this flooding and other things. This is, again, the plant I showed you. This is actually section 4, the new one. It looks really nice. Down here, you would see the Thames River. So one of the concerns with flooding is the river being at a higher point. So you can't really discharge any more effluent to the river because the river now is at a high point. So if you have to make your plant resilient, they put effluent discharge pump here. That's one they did. The other one, what they did is now they're putting a flood prevention structure right here around the plant. So this is like an example of a wastewater treatment plant that is really addressing climate change. So those two are obvious. I think they are more, in my opinion, engineering problems are being addressed by consulting. When we come to really research, my type of research, I look at these two or other. I call them process factors. With extreme, what really happens inside the plant, not around the plant, but inside the plant. Is anything changed inside the plant that I could help and resolve? This is an example, one type of extreme event with climate change. You'll have one, for example, of increased flow. So the potential of increased flow into a plant biological process system would be a biomass washout, process failure. Or sometimes with this high flow, you may have high loading. So there is a change in an actual loading of the system, which end up making your system not meeting target discharge water quality criteria. Now, for some of you who are familiar with this, you say, okay, this is wet weather event. We are aware of this. This happens on April, so why are you concerned? The reason why we are concerned is this is no more happening just on April. It's happening throughout the year. It's happening much more frequently than before. And that's the concern. It's no more like an event you would see once in a while. This is actually happening all the time. And when this happens, the question is, where is this coming from? You know, this is very specific to flow, but there is also temperature. There are other multiple parameters I'm not going to be talking about for now. But when it comes to flow, we look at, for example, a data that we get from April, and then we look at least 3 years of data for the month of April, and then we compare it with another 3 years of data that's coming from the month of September. So you can see in September, the flow is very much going into the wastewater treatment plant, very consistent. Whereas on April, we are seeing a lot of flows that are coming. So typically, when you take the change from the wet weather to the dry weather, that gives you a parameter called inflow and infiltration contribution. Those are coming from source and storm source. Even if you have separated storm and sanitary source, still you will get storm, which is the inflow, and infiltration is coming from the groundwater. So those, for me, that is known, and we design for that. In practice, we've designed a 30% factor for that, but what we see is actually it's way higher than that. And not just that it is high, it's also increasing. I have more data in 2022, 2023, 2024. So it's continuously inflow infiltration contribution is actually much higher. And this, remember, is from a system that gets its source from a separated source system. So, which is very interesting. Now that we establish what's bringing the flow, definitely if it is inflow infiltration, absolutely this is related with climate change. We know that. When this happens, how do plants respond in my area at the moment? So different plants have different strategies. From do nothing to do nothing means all the flow would come and then it will wash the plant and it will go. Do something, but that I don't like, which is the bypass. Meaning you could see this is an example from Toronto with all two of the Toronto wastewater treatment plants, the Ashbridge Bay and Humber. From 2021 to 2024, it's basically a bypass. So they have to dump it to a freshwater body when excess flow comes. So that's pretty much raw sewage in this case. You can see the amount, which is very much significant. That's why I don't really like that approach, but kind of better having that than just the plant being washed out. Other treatments, you can see auxiliary and this and that and so on and so forth. So there are plants who try to do a combination of things, but it is a big issue. That's what I wanted to show. And whatever plants are trying to do, it's all about using equalization basin, backup equipment, bypassing, dilution, all these things. And what are the opportunities for us researchers is actually we could develop more resilience framework around it, adaptive management strategy, use some digital tools to help us out, consider decentralization, I'm looking a bit of everything here, but because where I come from is on intensification technologies, so I'm looking on looking at biofilm-based technologies, how would they contribute to this? Because biofilm processes are resilient compared to suspended activated sludge processes that are mostly used by our wastewater treatment plants. So that is pretty much the problem around. And I also pull out, just to tease your mind, what about resource limited countries? This is data from the United Nations in one of the East African countries. So in terms of meeting the Sustainable Development Goals, so, you know, if you guys go and look at Sustainable Development Goals, it's different, right? Like, for example, drinking water, achieving drinking water doesn't mean you have a tap in your house. It means you are getting water within 30 minutes walking distance back and forth. Just put that in perspective, because when I see the first 70%, I'm like, no, it's impossible. But if it is like that 30 minutes travel time, yeah, that's potentially possible. But I'm also wanting to attract your attention here with respect to wastewater, almost no work done, you know? So remember, SDG 30 is supposed to be, SDG is supposed to be meeting 6, actually. We're supposed to meet it in 2030, which is what, 5 years from now? And this guy is gonna be expected to be 100%. So it is, when we look at from another country under resource development, this is way far. On top of this, what's coming into these regions is majority of these regions, this is from an East Africa region, they are moving into industrialization, and there will be more pollution. There is already more pollution. I have a project that I start working with. We are dealing with a lot of pollution, and it's going to be adding to already poor existing wastewater infrastructure there. And then on top of that, there is going to be this climate stress. So the situation would be difficult. I also want this team, because I don't have time, I can't go, but I want you guys really, I really want that to think I want you to do a picture what would have happened in First Nation communities here in Canada. So I share, the one I shared is for urban type of system, and then I shared here for an East African nation. I also wanted you guys to do something like this, but what would have happened for a First Nation community, okay? Just to understand the situation better. Now, solution-wise, I said, now I am developing a lot of intensification technologies. When I develop technologies, I intentionally look at technologies for, you know, urban area, you know, where there is enough resources. But I also develop technologies for remote communities, you know, for resource limited communities. So the rope type fixed film is really intended for resource limited communities. It is very passive, relatively cheaper compared to other biofilm processes that I know of. It's very simple, like when we operated here at our school, it's very much low maintenance, doesn't really require a skilled operator to operate this type of system. So when you develop technologies, you look at not only the cost of the technology, but also what does it require to run the system, because it's very important, right? So aspects of that are also very much reasonable. So what it is, as you can see, polypropylene. It's polymer loops. It has very much high surface area. And your bugs, your organisms that we use to treat water are meant to be growing on it. And as the water passes through this system, it's meant to be cleaned. You can see here in Canada, mostly this system is being used now in lagoons, which is majority of our lagoons are in the remote communities, which and the system under it has aeration diffusers already built to it. You just need to put it, and wherever there is a tank, you drop it and you connect it to a compressor or a blower for aeration source. That's it. It's very, very simple. And when the water flow will go either direction, it goes through here, and then it goes to the discharge point. If you need more treatment, you need to add more of this in your tank. The more of this you have, the more treatment. So why this is attractive for me for low resource setting? One, I have visited places. One of the issue low resource places have is sludge handling. This one, you don't need to do that. You know, there is no sludge. You don't even need a clarifier. You know, it's a flow through process. It goes in there. Any contaminant, majority what we look at is nitrogen and carbon, and get removed here, and then you can just discharge after that. Around this technology, as I said, we have been working with Bishop Water. We started developing the process, and Bishop provided the technology. Really nice collab we have there. We develop a lot of processes. As you can see, have published some, and there are some more. Majority of these are dealt with. We started the research from carbon oxidation. Can we do carbon oxidation with it? Yes, tick. What about nitrification? Can we do that? Which is ammonia conversion into nitrate, right? Ammonia removal. Yeah, we can do that. Now, okay, now that we know we can do this too, can we get some of this advanced wastewater treatment that we see all over? Can we bring this also and make it accessible to this infrastructure that could be used for remote communities? So that's what we have been doing, especially in the space of nitrogen. I don't know how many of you like this. I like this one. I'm not gonna go in detail, but I will just roughly describe for you. So if you have ammonia in your water, typically majority of the plants would require, they would have an effluent target to remove ammonia from the system. So the paths that we see in majority, I would say a lot of plants in Canada would nitrify, you know, so this can be discharged. And this process, as you can see, would require oxygen, which is aeration energy. That means an operating cost for the plant. So once you have nitrate, it's okay to send it to the freshwater bodies. But if you are sending it to a more sensitive water body, you need to convert this nitrate back to nitrogen, which this process would require actually an addition of external organic carbon source. So plants need to buy methanol and add that. Doesn't make sense, but yeah, we do that. So that process actually costs money and not really a favorite process. Another thing that you see here is this one, because it is oxygen, using oxygen, then you need, and then this doesn't, you should not have oxygen in it. So if you need to run, if you really, we call it to do a total nitrogen removal from your system, you need to have two systems. The first one would be aerobic to convert this to nitrate. And then you need to have a second one, which do nitrate to nitrogen. So it's not just only adding carbon when you separate them like this. They also need two systems. Now, if I think of this in terms of limited resources, it's you know, you are adding cost now. It's no more making it interesting. So the research I'm going to share with you guys today is how we came up with a way, okay, how about we do this in one tank? And then how about we stop adding this carbon? How do we come up with a system like this? So this process is called a simultaneous nitrification, denitrification. Those of you who are in wastewater, this is not a new process, I'm aware. It's just it's done in a completely different way than what we are doing it here. Because for us, our intention specifically is a low resource community. So we put that, as soon as you put that into perspective, you look at different things to develop this process. So some of the objectives we had around this is, the first one is understanding the how different inputs would affect the process, such as, the chemical oxygen demand, the COD, the nitrogen ratio, the dissolved oxygen, anoxic fraction, loading rates, so on and so forth. So again, why this is unique, why is this new or innovative, is because when you do it through one single stage biofilm process, these things get really complex, because some of the parameters behave completely different in the bulk liquid versus the biofilm itself. So all our previous understanding that we have on Metcalfe and eddy may not work. That's why we do this like as innovative research. Another one is, we also, now that you wanted to do all this in one tank, just as a flow through, you definitely need to create some aeration time, non-aeration time. How do you control that? So something has to turn on and off the compressor, the aeration, which supplies air. So again, this is where you can you can make your system expensive or cheap. You can go bananas by having all controls, expensive ones, which nobody would use them after a while because no one cleaned them. Or you can think of alternative ways of controlling it, okay? So that is something I could quickly share with you. And then the last one is a microbial shift. And Kelsey, please give me a thing if I'm taking too long, so I could kind of wrap it up fast, okay? All right.
You still have lots of time. You're good. Yeah.
All right. Wonderful. Thank you. And for those of you on the other side, if you have questions, please put it on the chat. I'm sure you know what to do. You have been doing this, but so the research, this actual research was done again at the Greenway wastewater treatment plant. I am a strong believer of using a real wastewater when you develop this type of processes and technologies, because it is completely different when you use synthetic versus real. I mean, synthetic is kind of okay as a proof of concept, but if you really are trying to do something that's of impactful, I know it's a lot of work to work on actual wastewater, but it just makes a huge lot of difference. I can tell you that. I talked something else. I wanted to show you guys this wastewater, relatively like strong wastewater for a North American system. Lots of COD and slightly high ammonia. Typically in North America, the ammonia would be 20 milligram per liter and the COD around 200. Ours is a little bit higher because a lot of industries actually discharge to this specific plant. The system we have, I will shortly share with you guys our experimental design, but what we have here is our test reactor, SND. My dream is, I have a wastewater, I just send it to this reactor, I remove carbon, I remove ammonia, I remove total nitrogen, and then the water is free of nutrients except phosphorus, of course, which need to be handled, and carbon. That's the intent. So just bring it here, the solid line. And so that's our one test. A second one we run in parallel is this purple one that you see. It's an aeration system because we just want to use it as a control. We want to make sure our ammonia removal from this system is meeting our guidelines, which is meeting similar to this. That's kind of a criteria for us. Even if we wanted to do total nitrogen removal to denitrify, we wanted to make sure the first and number one thing we want to achieve is ammonia removal. So the ammonia removal that we see here should be the same as this. So those are the two. So this is a control, this is a test reactor. And we have a pretreatment I will show you guys. It's an anaerobic reactor that we put in place here. That's kind of an afterthought, and I'll explain shortly. But remember, in all of these cases, this is a flow-through system. So there is no sludge recycle, this and that. So which makes it really attractive for remote communities. This is, I think, just a PFD, PNID. They're all the same tanks. The only difference is in SND, you have lots of sensors because we wanted to explore that. Where we did the work, here at Western, we had so much fun. Like we have a bay. We call it a demonstration bay. If any one of you make it down here, give me a call. I'll be happy to give you a tour. We have a bay at the Greenway wastewater treatment plant. We have 4 bays, and we can just, whenever you need to do testing, we can do a setup there, and you can directly get connected inside the building, which really makes it nice to do wastewater research because we don't need to transport wastewater back and forth, which makes it really easy. And also it's more like a demonstration scale. So you can get sludge, if you are working on water reuse, you can get secondary effluent from the plant. And we just basically have a pipe. You just need to get connected to this. In terms of the experimental design, we want to study factors, but we also wanted to look at controls. What type of control should we use? Timer control to turn the air on and off. Timer control is very easy, it's just simple. It doesn't need any follow-up from your side. It's very passive. It's a time, I want the air to come 1 hour on and I want it off for the next hour and I want it to come back the next hour. So you just need to set it up and forget about it, So the first 3 are timer controls. So to me, as far as a remote community go, this is a type of control which I can see working because it's hands-off, But it does work for most of the time. The issue is if your wastewater keeps changing, timer control is difficult. Because you develop that time on and off, it does impact your process. It is okay since it's constant. If your influent wastewater is constant, it's okay. If not, it's a problem. So to kind of assist that, and the problem is often caused by, we notice, or carbon. Then we added a pretreatment anaerobic system upstream for carbon control. We just want something constant that doesn't change. Of course, this will add another reactor, but on a good side, this type of process would have generated methane, which could be used within the community, because it's anaerobic pretreatment. So 4 and 5, where we have timer control, but we have also carbon diversion, we call it, anaerobic treatment for taking care of the carbon load. So I would say 1, 2, 3, 4, 5, really like good conditions to develop this process for resource limited areas. Now, the other ones, 6 and 7. 7 is what we commonly used in the industry in large scale systems, and 6 can also be used. So it's like, as you go from top to bottom, it means like from the first 3, I consider them as one timer control, then it goes to this, and then the cost of doing things is increasing. But obviously, it's always a trade-off. The main thing is, it doesn't mean expensive, doesn't mean you have to do it, right? It just means you need to know what you want and pick the right one. I think that's what this whole control thing is about. So what did we get? So the first one on the timer control, we have 50% anoxic, means we are turning the area on for 1 hour, turning it off for another another 1 hour. That's what brings the anoxic fraction. Anoxic fraction is the amount of time the air was off. So when we do that, I want you guys to really bring your attention to the water quality. This is a discharge water quality. What is that I want? I want when we started this, we said to ourselves, we need to get ammonia at least 5 or below. And then preferably nitrite would be another 5, the summation of the two. Preferably everything total, I don't want to, which gives you a total inorganic nitrogen. The total inorganic nitrogen being 10 or less. That would be the best. So depending, again, it's all about criteria of the system. What's the site? This type of things, we just show the framework, but the actual numbers is up to the site, right? So for us, when we look at that, the best strategy would have been the strategy where we did carbon management anaerobically with timer control. As you can see, during that time, your ammonia concentrations were within target. Of course, this one has a better performance in denitrification, but again, what is the plant looking for? So I think that's kind of one in terms of, because originally the understanding is timer-based controls, they don't work in real systems. And what we try to show here is, yes, they do work. If you are looking at this, I agree, it doesn't work. But what we added is a little bit another passive control, which is a carbon diversion. And that kind of helped it out in enabling this choice. Another one is, as expected, when you add more sensors, of course, when you add more sensors, your process is going to get better. The downside is sensors cost money. They need to be cleaned, and it's not a one-time fee, right? Like, because you need to change things maybe on a yearly level. But majority of my experience with sensors is you need an operator who really can take care of that. Otherwise, it's a waste of money. But coming back to the performance, obviously, when you have oxygen control, ammonia control, nitrate control, when all these things are properly controlled, you can get. I want you guys to really think this. This is like a flow-through system, It's like one single cell, no clarifier, no nothing. You just send, and that's it. Like your COD is out. I didn't even talk about COD. Or COD is gone. Your ammonia is gone, and there is no your nitrates and nitrites drop significantly. So this is like kind of, in terms of performance, I would say the gold standard within the industry. That's what you wanted to see. So with this, the next thing we did is we tried to see, like, model this system, and we looked at kinetic models. Like we use at Western Sumo, and we tried to model the system. It was very difficult. Again, why is it difficult? It just because the models currently are not properly capturing the oxygen fluxes within the biofilm. So when the model shows me, oh, you have oxygen in the biofilm, actually I don't, or the other way around. So one approach we did is, how about we try for now we have lots of data, how about we use some statistical correlation to see, and we just wanted to help design this system, you know, because just the factors are really complex interacting with each other. So we tried to reuse a regression, which did not work because of collinearity within all the inputs we have. So we moved into another multivariate statistics, the principal components. We have done other types of statistics as well. And we tried to come up with, ultimately, we just want to develop a model. So if someone has to design this system, how should they operate it? You know, that's what we want to guide. So as you can see, the model, I don't want to go into how the principal component analysis works, but we did put all the inputs. Ultimately, we have some linear model, which based on the R square, it's, I would say for this type of process, it's a good R square, and which can help, you know, designers just to pick some operating conditions. This is kind of a temporary fix. Of course, we need to deep dive into kinetics of things and really tweak the actually the mechanistic based model to help us design this better. But for now, I think we have a linear model which is developed based on data really. Another we did on this work is microbial population. Just, I'm not gonna go deep dive into this one. It's more of, you know, confirmation of what we did, you know, what's that I wanted to see. For example, we have pretreatment. We were worried about that because the tank was open and we were like, do we have other like bacteria that makes use of oxygen and this and that? So we use this for in our lab more like as confirmation, because if you just simply base everything based on input and output, there is this black box effect. So it would be nice to see who is actually doing the work for us, you know, from that perspective. That's how I use microbiology, guys. I'm not a microbiologist, but I like to see what's in the system. So you could see when you look at pretreatment, it is anaerobic, and heterotrophs, they should be there because they make use of carbon. And the yellow one, it's the denitrifying bacteria. That's also heterotroph. What I was wondering about was, are there things that make use of air, which for nitrogen removal, which are mainly the ammonia oxidizing bacteria and nitrite oxidizing bacteria? Both of them, they don't exist here, so it is great. And then we come to the aeration. You can see those, by the way, these are relatively slow growing. That's why you see a lot of heterotrophs, which is fast growing, but I know they're not that much, but they're very much efficient. So do a good job. The surprising species is actually Anamox here, which is anaerobic ammonia oxidation organism. We found those as well in our system. We have other research where we look at, you know, some processes called partial nitrification Anamox, partial denitrification Anamox. We have those. I brought SND here, but we do those as well. We develop those processes using this technology. I think that's pretty much it. Just to give you guys a take home, what we got out of this. I think for me, the take home is, yes, in a flow through process, you can achieve simultaneously carbon removal, ammonia removal, and nitrate removal, which is great in a flow through process. And control strategies in a single tank. You could do this in 2-3 tanks, which is okay. But if you have to do this in a single tank, either you need sophisticated sensor-based control, or you need to use a basic time-based control with some kind of carbon diversion. And the carbon diversion is very interesting for remote communities because of it's converting the carbon into energy. So that's another attractive thing. I think the others are more PCA analysis. You know, someone may replace this with AI if you are interested. We thought we don't need to do AI because it's very much straightforward relationship, is very linear. That's why we mostly do it parametric study using PCA, and we were able to achieve important factors from it and understand what influence, which factor influence this process more. Also, it helps us to come up with a simple linear regression type of equation that would guide design. And microbial community also helps us to confirm process really. Finally, you know, I'd like to thank all the collaborators, but my amazing students who let me talk and don't let me work on it. I really appreciate that. And yeah, that's where we are gonna go, just quick notes, where we are gonna go into this process now is we literally have developed basic and advanced wastewater treatment processes using this technology. Our next stop is looking at resilience. So we will be looking, that's actually, I have a PhD student. Do I see her here? Oh, no. Yeah, that's her. She's working on resilience of this specific system. And Lynn here is actually the one who did all this work on the SND. He's currently a postdoc in my team, and I know he's in the IWAYP. He's very active. Probably some of you have met him there as well. And yeah, that's pretty much it. And I also like to thank you for WASH Canada to invite us, and absolute big thank you for Bishop Water for collaborating with us. And pretty much done.
Yeah, thank you, Martha. Thank you so much.